Hi, I am Alp Nuri Akdağ, and I'm going to talk about my thesis topic, Runge-Kutta model predictive control of 2 degree of freedom helicopter system. We will start with an introduction and explanation of the methodology. Then I'll start with explaining model predictive control, then Runge-Kutta system identification, helicopter dynamics, Runge-Kutta based model predictive control architecture, and finally, I will talk about the results and conclusions. Feedback control is crucial for achieving precise tracking of time-varying reference trajectories. Traditional controller structures often fall short in handling complex control problems. Model predictive control addresses these challenges by incorporating future system dynamics and generating optimal control signals. This thesis presents a novel proposition for the employment of Runge-Kutta-based model predictive controller architecture in addressing the control challenges associated with nonlinear multiple input, multiple output systems, with a specific focus on flight systems, such as helicopters. The research endeavor is structured into 6 cohesive and comprehensive sections, as you can see in the figure. Model predictive control predicts future system behavior using a system model and the correct prediction and control horizons. An objective function is optimized, minimizing the tracking error. Model predictive control handles constraints, nonlinearities, and time delays effectively. It is suitable for multivariable systems, optimizing control signals across multiple inputs and outputs. Our objective function minimizes tracking errors and control signal derivatives. Prediction horizon, control horizon, penalty term, constraint functions, sharpness, control signal range, and offset contribute to minimizing the objective function. The elements of the control vector are adjusted based on the general update rule, ensuring they remain within the permissible range. In steepest descent method, we have P equals minus G, where G represents the gradient vector needs to be computed. Now let's talk about the identification method. Consider a multiple input, multiple output nonlinear system described by a set of differential equations in a compact form. The system can be discretized using the fourth-order Runge-Kutta integration method. This discretization allows us to obtain an iterative system model for control purposes. By repeatedly applying the obtained states as models output, an iterative system model can be obtained. As can be observed from the discretized equations, the system requires the state vector and the system parameter vector. An extended Kalman filter is used for state estimation, and the parameter estimator based on the Runge-Kutta method is proposed for the calculating the system parameters. Thus, by utilizing input and output data of the system, the Runge-Kutta model of the system can be easily constructed, as shown in figure next. We use the 2 degree of freedom helicopter system, and these equations represents the helicopter dynamics. We want to control the pitch and yaw angles of the helicopter. Now, Runge-Kutta based model predictive architecture. The input signals iteratively applied to the Runge-Kutta system model to estimate the kth step dynamic behavior of the system and kth step Jacobian information. The primary objective in the structure is to minimize the following objective function. For the minimization of this objective function, the term that needs to be updated in the control vector is obtained using a Taylor series expansion. The second-order Taylor expansion of this objective function is derived as follows. Here, Jacobian matrix and error matrix are shown. And finally, after all these simulations, the system couldn't achieve the desired reference tracking. So what this say about our purpose? In conclusion, the results obtained from the implementation of the control system were unexpected, as the system couldn't be effectively controlled. However, it is important to acknowledge that this research has provided valuable insights into the shortcomings and limitations of the control system under study. Thanks for listening.